Alright, hey you guys, this is just a walk through the key that I provided for you. See if I can give some more insight just by talking through it with you. Thing about critical values, in case you were still wondering what on earth this critical value thing is, it really is just about, for our purposes, where the first derivative is equal to 0. It's also where the first derivative is undefined, things where you're dividing by 0 or if you have some other interesting happenings, but we'll just go with setting the first derivative equal to 0. One of the things that commonly happens is you have to factor. So here's the first derivative, using the power rule on here, power, bring the exponent out front, subtract 1 from the current exponent, and so on. So hopefully that looks familiar. And then when you get to that derivative, it helps to factor so that you can easily find out where it's 0. So if I divide an x out of each of these terms that I've put in here, so I divide x out of each of those and put it out front, it leaves behind 3x minus 4. It's the same expression, so it's still equal to 0. That easily shows us that pretty plainly that one of the things that will make this equal to 0 is if I set x equal to 0. The other is some value of x that would make 3x minus 4 equal to 0. You'll find out they're different values. X equals 0 is not what makes 3x minus 4 equal 0. Turns out that that's 4/3 that you see over here. So when you get done factoring, you're looking for the values of x. Now there are 2 of them in this case that would make this expression equal to 0. So once you get those are the critical values where it's equal to 0, because this doesn't have any issues with where the first derivative is undefined. With those critical values, those are your stopping points for your intervals of increase and decrease. So when I say what are your intervals of increase and decrease in part B, well, they're going to increase or decrease up to a critical value, and then increase or decrease to the next critical value, and so on. You'll continue on. So in this case, it's negative infinity to 0, we're increasing, and then also from 4/3 on to infinity. And you can see that here if I look at those portions of the graph. The other place, the downhill portion, so if you see right here, call that the interval of decrease from 0 to 4/3, and that's it. You just write the expression that way. Next problem. Okay, so this one, sorry, it's a little bit small, but I just wanted to just quickly annotate what's going on in here. Same thing for number 2, it says find the critical value, so it's the derivative first, set it equal to 0, and what you do from there is the factoring piece. I can divide from each of these. Notice they have an x in common and a 4, so I literally divide out of 4x from both of them. When I do that, what leaves behind is x squared minus 12. So x equals 0, the outside expression 4x, what would make 4x equal to 0? If x equals 0. What would make x squared minus 12 equal to 0? X squared minus 12, set it equal to 0 and solve. That means add 12 to both sides and then take the square root. So I get 2 values, plus or minus the square root of 12 or plus or minus 3.46. So the idea is what would make either one of these pieces of this product, 4x or x squared minus 12, equal to 0. I got them both. 0 and then plus or minus the square root of 12 for the other. So that altogether is 3 critical values. I graph those, so on the intervals of increase and decrease, so you can graph this thing. We did it graphically on the previous page. Well, now I'm using this first derivative test where you use the critical values, you place them on a number line. And then what you do is take the first derivative and you test numbers in those intervals. To the left of negative 3.46, I have chosen negative 4. You can choose anything to the left of negative 3.46. And what you do is you put it into the derivative, you calculate what you get, but all you really care about is the sign of it. In this case, I get negative 256 plus 192. I know that's negative. Okay. Then between negative 3.46 and 0, test an easy value in there like negative 1. So I chose negative 1. Some number between those two values, put it in the first derivative. I get out negative 4 plus 48. That's a positive number. So if you notice, I've notated where it's positive or negative up above here. But the work for the derivative between 0 and 3.46, the other critical values here, I put in 1. Substitute that into the first derivative, get out 4 minus 48, which is negative. So I've indicated that up above. And then after 3.46, I chose 4. You can choose any number in those intervals. Those are just values that I thought would be relatively easy to work with. The result of that is positive. You see it here. Wherever it's positive, that's an interval of increase. Wherever it's negative, it's an interval of decrease. And that somehow did not make my key when I put that out to you guys. So hopefully take a look at that. The intervals of increase specifically are from, let's see, negative 3.46, if I use the decimal, to 0, and also from 3.46 to infinity. Make sure you have that. And then the decrease, and I'll remind you guys of this before the test tomorrow if you happen to forget, is negative infinity to that negative 3.46, and also from 0 to 3.46. And you notice I'm getting that increase I'm getting from looking at the positives, and decrease I'm looking at the negatives. Okay, moving on down to the bottom here. It says for problem number 1 on the first page, find the point of inflection using the second derivative. Well, point of inflection, we just briefly chatted about that the other day, just a couple contexts, is where the second derivative is equal to 0 or undefined. So we'll just stick with where it's equal to 0. Okay, this is the second derivative. That means taking the derivative not once but twice. So if we go to the first problem, take its derivative, we got this. You'll see it there. Then take the derivative again, and we get this 6x minus 4. To solve that, when it's set equal to 0, you add 4 to both sides, divide by 6, and we get 2/3. And if you look at the graph on the first page, if you go back to that, you actually have this inflection point. You'll notice it's where the graph goes from being concave down to being concave up, and you'll notice that happens just as we found at x equals 2/3, very precisely. And looking at the graph, it's a moment of greatest decrease. I asked which of the above is satisfied. In this case, it's a moment of greatest decrease. And do use the graph, and I'll provide one for you tomorrow on the test as well. And the last page is talking about maximizing profit. Find the rate of change of profit when a month. I'm sorry, this is the related rates problem. So now we're not maximizing, but when is find the rate of change of profit. In this case, that means we're going to do implicit differentiation, and profit is not an easy function to take the derivative of as it's written up here. But if I do a little work and simplify it, I can get to this expression here. So take a look at the work above. It's just distributing the x, then distributing the -1 to both terms. You want to make sure you get to both. That's important. That's a pretty nasty little arc that I threw in there. But that's the big key, is that you just have to be able to distribute to both terms and do that really carefully. Then you get that expression that I've circled over there, and the derivative of that you see here. And then from there you're going to decide where to plug in. So implicit differentiation, remember, is anytime you take the derivative of something with, since we're doing derivative with respect to t, anything we take the derivative of that doesn't have a t in it, like an x for instance, you have to put dx dt after it. So derivative of 1940x is 1940. Don't forget dx dt, because it was an expression with an x in it. Then when you're done taking that derivative, and you've got this nice little expression, you want to make sure you then go and substitute in the values that are given. X is 500, and then dx dt, it's not explicitly written as dx dt, but it says change of sales in 70 units per month, or is 70 units per month. And sales, if you notice, if you go back, x is a representation of sales, and month is time. So that's definitely a change in sales with respect to time, dx dt. And if I see that expression here, everything's substituted in nicely. Use a calculator and you can get the $134,680 per month increase in profit for those given values. Down at the bottom, just some implicit differentiation is just taking the derivative with respect to x, and you get that from looking here at saying find dp dx. So you derive with respect to x, so dp dx, because it's not an x, you have to write that. Derivative of p would be 1, but dp dx is important. Derivative of x squared is just 2x because it's with respect to x. And derivative of the constant 150 is 0, as usual. Solve for dp dx, which is pretty simple in this case. And that's the part A. Part B asks you to plug in the values, and x is 11. That's the only thing we have in our dp dx expression is -2 times x. So if you put that 11 in there, you get -22. Down in number 62, here's in a simplified expression here. Instead of square root, you should use 1/2 while taking the derivative. So finding dp dx in part A is to take the derivative of 1/2 p, which is 1/2 dp dx, plus the derivative of x to the 1/2, which is just 1/2 x to the negative 1/2. Derivative of 30 is 0. So you see that here. The baby's waking up. And so after you take that derivative, you want to make sure that everything looks kosher in here. We're going to solve for dp dx, right? That's our goal. So I want to subtract away the 1/2 x squared to the negative 1/2. You see here and here. Do it to both sides. And then I have to get rid of this 1/2, and so I do that by multiplying by 2/1 on both sides. And that gets rid of the 1/2 you see by dp dx. We want dp dx by itself. And so I might put that here. Cancellation. Isn't that great? It's cathartic to do that. And then finally, dp dx is alone. And what's left behind is negative x to the negative 1/2, which is fine. You have to understand that's also the same as negative 1 over the square root of x. Our x, if you go over and look at the givens, is 400. I just covered it up. So if I put 400 into that expression, you'll see that here for x. It's negative 1 over the square root of 400, which is negative 1 over 1, or over 20. And that ends up being the end. Hopefully everything is a little more clarified in the video, but do email with more questions.